Yeah, so maybe then we resume whenever you are ready.
Okay, I'm ready. If I can
Yes,
be. Okay,
I
very
think
good.
we have most of the yeah of the participants. They didn't go out of the room. So let's continue then with the next talk of Thierry Paul, and he's going to give us a talk about the mean field limit for hybrid models of collective motions. Please.
Okay, thank you very much to the organizer to have invited me to this fascinating conference. There are so many subjects. It's very interesting. And so what I wanted to talk about today, some results obtained in collaboration with Roberto Natalini at IAC in Rome. And I would like to consider the mean field limit for models which are coupled to some chemical activity at the lower scale, so to speak. So let me just start. So talking about scales, usually we talk about scale, which in mean field theory, which comes from biological or, so to speak, sociological, I mean, particles into macro and macroscopic scale, and which is exactly the spirit of mean field and particles. Basically, you average about all the particles but one, and then you look at the dynamics of the result. You have the result is one particle theory, self-interacting with itself, and then by this you pass from an n-body dynamical system into a kinetic phase space. If you go a little bit further in this direction, you want to pass from macro to physical space. That is not to have a phase space anymore, which is something that you don't see really, but to pass to physical space, that is passing from Vlasov to Euler. But the novelty of what I'm going to say today is about that I want to add another scale, which is below the scale of particles, which is interaction with a chemical medium, or it can be also a social medium. In fact, I will not, my talk will not be very precise in biology because I want to focus on mathematics. And this interaction with chemical method consists in having contact with a particle with a medium, with a medium, diffusion of density of the medium, and a sensitivity of cells or particles to the gradient of the density, because in biology, apparently cells detect the difference of the densities. So this creates a force, which is a gradient force, where the potential is played by the density of the chemical. And of course, there is also another scale or another feature on the other side again, which consists in inverting the velocity part of the Euler system in try to go to a Keller-Siegel, but this work is in progress. I'm not going to talk about that today. Okay, so the models we looked at was a model where you have n particles in d dimension of space. That is, your phase space is in R2dn. And I have a first part, which is inertial part, like usually. And the second part, which is given by a force, Fi. And we start by an initial condition. And this force will let intertwine some kind of collective interaction. And I put it as a function both of the velocity and the position. If you have only position, then you have a two by two interaction potential, and you have in a Hamiltonian setting. And if you take for gamma a function of c times, for example, just the potential v, the value of the velocity, you get the Cooker-Smale famous models of collective motion, which leads to flocking and etc. But I'm not going to specialize on flocking. I'm going just to take a general interaction like this. And the hypothesis on gamma will be that it has to be Lifshitz and sublinear in V. Now, what we want to add is another force to this force, which also is a gradient of a certain potential at each point x. We could also add an external force, but for the talk, I won't consider it. And this density here, this potential, chemical potential, follows a diffusion equation, where you have a term of diffusion here, you have a term of reduction, which of the degradation, because after basically the chemical product acts with the cells, there is also the action of all the other environment which give you a degradation given by this. And the most important is that you have a force. The force depends on the point X, which is interaction between the point X where the chemical potential is evaluated, with all our dynamical system XC. And in fact, we choose this source term of the form f of x and all the x, no v, but just the x of the full dynamical system, in this form that is an average basically of a cutoff function key, which is compactly support, which is basically count the number of particles which are in the vicinity of x. So basically this source term is just reflects the average number of particles of the dynamical system which are close to x. So having in mind this type of model, I'm going just to start without the chemics and to talk very briefly on some earlier result we had with Roberto concerning the Cooker-Smale type model. Oh, sorry, this is a mistake. This shouldn't be here. And this time we take no chemist and just a closed dynamical system like this. One knows since I think Tadmor and Ha and Tadmor in 2008 that there is a Vlasov equation associated to this, which is easy to derive, to guess, because it's just as a Vlasov equation, except that you have a convolution also on the velocity, because the interaction depends on velocity. And the transition between this equation to the Vlasov equation had been I think, proved the first time with Ha and Liu in 2009. And sorry for the people in the audience who work on this, I didn't note because there are a lot of other papers to the derivation. But up to us, I guess, all the derivation were using empirical measure. So in this slide, I would like to compare a bit empirical measure with respect to marginal methods, which is another way of deriving mean field limit, in particular that we used with François Gols and Clément Mouot in a paper. I will go back about it a little bit later on. So what is an empirical measure? An empirical measure is a measure which is indexed by a point in the n particle, n body phase space, and which depends to one body phase space x and v. So it's a probability in R2D indexed by a point in R2dn. And it's done by just a sum of delta at the different points in the large particle coordinates. So of course, the transition between the n particle dynamical system and the Vlasov equation is given usually because, of course, any rho in can be approximate by some empirical measure like this, because if you put more and more points by summing delta, you can get a continuous, or no, not even continuous, a measure of any kind. And this remark, plus the stability of the Vlasov system, which was settled by Dobroshin, indicates you that if you evolve the parameter x and v by the flow, so the general flow, you get something which is a function of rho of t of one particle, which follows the Vlasov equation. Now, the problem is, why is it maybe interesting to find some alternative methods to derive the Vlasov equation, is the fact that this is absolutely non-quantitative. That is, for a general measure rho in, you know that there exists empirical measure to tend to this, but if you want that it tends in some topology with a certain rate of convergence, it's very difficult to know if we want to keep the most freedom you can on rho in. In fact, you know that it's true basically almost everywhere, but it's almost everywhere when on a space of dimension at the limit where this dimension increase. So it's a little bit tricky. In fact, the true formulation as far as I know, has been given by Fournier and Guillain. So the paper is published in 2021, but it was no, sorry, that's a mistake. It's from 2015 or something like this. And it tells you that if you take a probability measure with finite second moment, then if you compute the Wasserstein distance of order 2, it works also for other Wasserstein distance, but I settled the more simple case for the Wasserstein of order 2, between an empirical measure pinned up at any point xv and the rho you have it. So this object and this object don't see us a priori, but if you integrate this, that is, if you integrate this with respect to the nth tensorial product of rho over the dx dy which are here, you get something which is small when n goes to infinity. So this tells you that basically almost everywhere you can approximate this by this at this rate, but it's only in average about rho to the n. The alternative method consists in looking at the n-body Liouville equation associated to the full dynamical system. That is, you take a solution which is given by the push forward of your initial condition by the n-body flow, and to associate to this rho n its third marginal, which consists, if you started by a rho in, which was symmetrical with respect to permutation of particle, and we'll be fast on this, you integrate over all but one points in phase space, and you get something which is a function of one particle now. And we know that, we can prove then that this rho n1 tends, when n goes to infinity, to a solution of Vlasov. I'm very fast here because I will come back immediately after. So you can imagine to wonder what's the link between these two approaches, because these two objects are very different. Here you have a kind of Lagrangian approach where you look at the trajectories and you look by fixing one point in phase space, how the trajectory passes through this point. So that's more or less the spirit of empirical measure. Here you have a more Eulerian way because you look at the big equation for the n-body Liouville, you compute the marginal and you find the Vlasov. In fact, there is a link, and let me mention it because I think this is starting point of the quantum version of empirical measure that François Gold is going to talk about this afternoon. In fact, the link is very simple. What is the link between empirical measure and marginals? Just the fact that an empirical measure, when you consider it as a function of one particle here and the parameter, which are the n-body particles, this is the integral kernel of the map which associate to an n particle distribution its first marginals. So in fact, there is a kind of functorial fact which relies to, but in a computation for empirical, for mean field, for classical mean field system, this is not something which is so much used, I would say. Anyway, in the rest of the paper, I will take definitively this part, this approach concerning of marginal, although we will have to use the Fourier-Guillain theorem in several steps, and I'm going to explain you this now. Let me look at the time. Okay, so I have to. So the theorem we have, when we don't have chemistry, is if we take Lipschitz sublinear, if we take an initial condition of the n-body Liouville system, which is just the tensorial product of rho in, which is compactly supported, and this is a change with respect to the formal result, but it's absolutely neat for us. If you look at the solution of the Vlasov equation, I call psi phi t the flow defined by the n-body particle system, when the first marginal, what we have is that the Wasserstein distance of order 2, which I'm going to define right now, between the first marginal and the solution of the Vlasov equation with the same initial condition, is of order n-1 times a CT. This CT, if you look at a gamma which doesn't depend on velocity, this CT is just an exponential. But because it depends now on velocity, it's a little bit more tricky. And in fact, the value of CT is quite horrible. This is why I wrote it in a teeny scale. But what's important is that the CT depends on the support of rho T. So it depends on the support of the solution of the Vlasov equation. And this is why you need to start by a compact support. Of course, the compactness of the support will be preserved, but the support will increase. And this is this increase of the support which will drive the CT. But I'm just a little bit fast on this because I want to go to the chemical part quite fastly. So here's the definition of the Wasserstein of order 2. It's the infimum over all the coupling meeting the probability measure on the product space or the space where lives the two mu and nu. So you take all the couplings, that is, a coupling is something where that when you take the marginal with respect to one factor, you get mu, and the marginal with respect to the other factor, you get nu, and you integrate this cost, which is given by the integral of x minus y over squared of gamma of dx. I guess most of the people know this very well. So the proof in this case, it's pretty much related to the paper with Goltz and Moore in 2016, which I must say was itself after some work with Goltz, Moore, and Ricci two years before. And there are two differences: the dependency in the velocity, and the fact that it depends on the velocity is unbounded, which is fundamental for the Cooker-Smale motion. So this gives you the complicated CT. But I want to say, comparing to the other derivation of Vlasov or Cooker-Smale, that we are not exactly with gamma, which is Cooker-Smale. We just impose that the collective motion is a gamma, which is a Lipschitz, can be anything. So in particular, we don't use absolutely no use of flocking in order to get this result. Okay, now let's come to the coupling with chemistry. So now we have the same part, of course, for the inertial term. And then we have a force, which is the same as before, but now we add, so this gradient force, once again, which is a gradient of something which is obtained by diffusion after a source term which coupled the source. So you see this equation is coupled to this one, and this is this coupling which makes the things interesting, at least. So the main difference, absolutely the main difference between the approach that we had for the case where it was no chemistry comes from the fact that there is no UV equation associated to this. That means that this defined, perfectly well-defined flow, of course, but if you look at the push forward of this flow, push forward by this flow of an initial condition, this push forward doesn't satisfy the closed PDE. This comes because here you have something which depends precisely on the trajectory. And this cannot be expressed as some part of the solution of the Liouville equation, if any. So we have, in fact, the new thing is that you have an equation which is not only non-local in time, but it's also non-time, sorry, it's a mistake. So we deal with a system, and a hybrid system, which is non-local in time and in space also together. So what is the theorem now? So I have the same hypothesis on Lipschitz function. I have an hypothesis I didn't notice, is that this function key here has to be also C1. Probably Lipschitz would be enough, but let's say C1. We look at rho in, which is also factorized with compact support of the factors. We look at the solution of the chemical Vlasov, which I didn't introduce yet. How come that I didn't introduce? Sorry. Okay. So associated to the system, sorry, I should have put that before, we will have a Vlasov equation, which will have this first term is as usual, but you add once again a force of this form here. And this now is going to be exactly given by a diffusion equation as we had before, except that here, instead of having something which deals with the trajectory, since now there is only one particle, this is going to be just the convolution of the function which captures the cells around the point X with the function itself. That is, this is the Vlasov equation that, which corresponds to our system. And indeed, what we prove is the fact that the Wasserstein distance over the two between the push forward by the flow and the solution of the Vlasov equation is small when n goes to infinity with different rates depending on the dimension d times a certain time-depending coefficient that I don't mention here. So this gives you exactly something which is in a certain sense close to what happened with without the chemics, but there is also a result which corresponds to the evolution of the chemical part, because you see our system in fact has two unknowns. The unknown are the flow here, but there is also the unknown which is the chemical potential which evolves with time. And this time what you get is that the chemical potentials that you would get by starting from the particle system minus the one that we started with the Vlasov equation, you have an estimate of the form that in average with respect to the initial condition of the L infinity norm of a square. That is something which is a little bit like we had in the Fourier-Guillain stuff. And this is, and then you have a decay exactly that way. The reason for which we have something which is not involving the Wasserstein distance is the fact that you see here, when you look at the system by itself, you have a phi of t which correspond to something which starts with a position on phase space. So this is difficult to accept through empirical measure, basically, to compare to a continuous or a measure as an initial condition. And this is where you get something which is of the former Fourier-Guillain theorem. Okay, so of course we have no Liouville equation, as I mentioned, except if you start by, for the n-body dynamical system, by an initial condition which is just a delta. So this is not an empirical measure. This is a true delta in n dimension, that is in 2dn dimension, and you symmetrize with respect to permutation here. Then you see that the fourth term is going to be exactly of the form, that is exactly these things here, but it's also be equal between the convolution of your step function key with the first marginal of rho. Just a simple computation you get. So this is why leads, in fact, to imagine that the Vlasov equation, so you mistake here, the Vlasov equation would be exactly this one. That is, you would have something which involves here the first marginal, and then passing to the limit, it would be just a function of the Vlasov. So this is why this is suggested by this. So this intermediate step we consider by taking, by the intermediate step, I mean this one, that is, you have here the dynamical system, but now the force, instead of involving the trajectory, you have this one where, where the force involves the first marginal of the solution of the Liouville equation here. So estimating the difference of solution between the particle system and this Liouville Vlasov will be one trick. The other one will be to estimate the solution between the Liouville Vlasov and the solution of Vlasov, and then use the triangular inequality. So in fact, associated to this original system here, we have at the other extremity the Vlasov equation, and in between we have something which is of the form of the Liouville equation, just because you replace the source term by the source term involving the first marginal. This is a trick in order to get something. Now, how do we prove this? I think I'm going to be also early like Cyril, probably because we're all very tired. So first of all, what we have to prove is that the three dynamics before this three dynamics here exist. So the first system was in fact introduced by Costanzo, Menci, Messina, Natalini, and Vecchio, and it was proved that you have global existence and uniqueness, and thus the hypothesis on gamma to be Lipschitz and sublinear in V. Now, for the two other equations, we have to prove an equation that we have existence in uniqueness and also a Dobrushin estimate. And we have, in fact, existence in the space of continuous in time. With respect to here, we have probability with compact support. And for the chemical potential, we have W1 infinito. I'm not sure that we are really sharp, but we can prove this. How do you prove this? Well, we extend, in fact, once again, a result by Piccoli, Rossi, and Trella from 2014, which was dealing with, so to speak, general Vlasov-type. And we extend in the case of not only you have non-locality in space, but you have also non-locality in time. So this is included in our paper. And I just put back the definition of Wasserstein here. So one of key results in order to prove this, which that we used after as a black box, is the following. Suppose that we have two PDEs of Liouville type, which are given by two forces, two potentials, two vector fields, VI, V1, and V2. Two equations like this. The two VI here, I don't put all the dependence, but it can also depend on rho I. And not only depends on rho I, but depends on the whole history from 0 to t of the solution itself. So it's very general theorem. We suppose that nevertheless, you have this bound when V tends to infinity. Then what you prove is that the distance, the square of the distance between two marginals of two initial conditions, ρ1 and ρt, first marginal is bounded by one thing which actually will be 0 if you take ρ in 1 equal to ρ in 2, plus 2 over n, so it is something small, and this integral which involves one of the solution here times the difference of the two vector fields here. So as soon as you have something like this, in fact, this computation, it's a computation we did it in the paper with François and Clément, but we didn't extract something like this. But here, since the situation is much more complicated, we had to do it in a black box, and we prove it in full generality that we have something like this. In other terms, if you want to compute this one, or to have an estimate like on this one, you have to basically estimate this difference of the two vectors on average with respect to one of the two solutions. So how do we prove this? In fact, what you do is that taking your two initial conditions, ρ1 and ρ2, ρ in 1 and ρ in 2, you will propagate an optimal coupling of these two things, optimal with respect to the Wasserstein distance. That is a function of xy, since it's a coupling, it's you double the number of variables. So it's in variable x, v, and y, and xc, in a sense that if you integrate over x and xc, you get this one. And if you integrate over these variables, you get this one, just a coupling, and you suppose that it's an optimal coupling. First of all, you can prove that if you evolve like this coordinates by one of the equations, this second coordinate by the other equation, you still get a coupling of the evolve ρ1 and ρt. But of course, this coupling is not optimal anymore, but still a coupling. Now, when you compute the cost, that is the integral of the cost function with respect to this evolve optimal coupling, and this evolve coupling, you have integration by parts just because you have a conservation law. You see, the equation you put in a conservation form, so you can put the integration over here and over here by integration on the cost, and you get that since the cost is quadratic, you still have something quadratic, and you make some kind of algebra manipulation, and you find that you can reconstruct the cost like this. What does it give? It gives you that, in fact, since you want to use a Grön-Van Lehmann at the end, what you need, the only thing that you will need at the end will be to compute the integral of this part of this with respect to the coupling. But since you reduce this exposed at the same point x and y, x and v, and x and v, you will can perform the integral over dx and dx over the optimal coupling, and this is what you get. The rho in here is the only one. Okay, so I don't want to be more precise on the proof, but this is very helpful for us because then, since we have several cases for V1 and V2, we can use it as a black box. So what remains is to estimate the 2V, that is the two vector fields correspond to the particle system and the Vlasov-Liouville, and the two corresponding to the Vlasov-Liouville and the Vlasov itself, because we decided to separate the estimation in two. So when you go from particle system to VL, what you get after a lot of computation, there are several pages of computation, it's a little bit complicated, but finally you get this, that is, you have to just estimate the difference of the two potential, and by now a lot of some computation, you found that finally, thanks to the theorem, you estimate the two solution for the particle system and for the Vlasov system as something which involve the Fourier-Guilhem constant dependence in n, just because at one point you have to reintroduce an empirical measure. So in our proof, the empirical measure is not present in the results, so to speak, but is present in the proof very much. And you use this Fourier-Guilhem, which I remember tells you how you can approximate on average any kind of empirical, any kind of probability measure with respect to an empirical measure. Now, for the other term, you have to estimate now this part here. I remember that the phi, psi, and large psi were just the chemical potential in the three dynamics we had here. This was a particle, this was for the Vlasov-Liouville, and this was for the Vlasov. So, so for the second one, we do that, and this, in fact, you cannot estimate ex nihilo, but we estimate it in terms of the Wasserstein distance of the two solution itself. So you end up with something like this, that you know that what you want to estimate, it's smaller than a constant times an integral of the square of what you wanted to estimate. It's not a quadratic Grunwald, because here you have just W and W, and you have the square, but you conclude by Grunwald lemma, and you find the things. Now, in order to get the result for the chemical potential, remember that the chemical potential was in fact solving the heat equation with source term, a kind of convolution of rho with a certain key. So if you do that, you will use now that in L infinity norm, the solution of these two diffusion, the difference of the diffusion of the two initial conditions is bounded by the Wasserstein distance of rho and rho prime. So the lemma is this one, and you use it, and this is why finally you reduce to have some W here. You have to approximate this by an empirical measure, and this is why you get the result. Once again, Van Fournier, not Fournier, Guilhem. Okay, so I've been very fast also, but I see nobody will blame you if I finish a little bit in advance. And it's very strange on Zoom because people are supposed to laugh now, but I don't hear anything. Anyway, let me finish by looking at the monokinetic ansatz and how we define an Euler-type equation in this case. Now, suppose that we start our Liouville n-body Liouville equation by the tensorial power of a rho in, which is of a function like this, that is monokinetic, that is, you have a density in x times a delta of v minus a velocity field in x here, the usual track. Then we can prove that monokineticity is almost preserved in the sense that you can compute the first marginal of the evolution of your initial condition. This is going to be close to another monokinetic distribution like this, with the same rate of conversion than before. And this is going to be valid for all times such that mu t and mu t are the unique solution of the Euler-type system, which consists in, it's a little bit like an Euler system. You have here the first part. Here you have something which is involve a Vlasov-type equation. So without this part, this system has been studied, and I will tell you just in a while. But then here you add the chemical potential, once again coupled to the solution by this equation. I mean, coupled to the amplitude solution here. So the system without this chemistry, this system has been studied and proved the existence in illness by Figali and Kang, and also Carrillo and Choi, 2020, but I think the paper was much before, I don't remember exactly. But we didn't look really very carefully about the fact that this system with the chemics potential has the same kind of properties and the one without here, but we guess that it's true. And we get also an estimate, of course, for the potential in terms this time and an average about just the rho in here, not just the amplitude and not the whole solution, just because we have this monoticity type, and that the chemics couple just the part in physical space. Okay, I think I'm finished now. What could I tell you more? Well, to enter more in the details would be probably boring, and also it would take much more time. So, well, I mean, if the chairman is okay, I will stop here.
Yeah, sure. Thank you very much. Thank you, Thierry. Okay, so are there any questions in the audience, please? Please. Yeah. Okay.
Yeah.
Yeah, go ahead.
Hi, Thierry. Thanks for the talk. So I have a question. So here, the fact that you consider initially tensorized density, a tensorized endpoint density is crucial to benefit from the Fournier-Guillain quantitative estimates, I guess.
Yes.
And would you have more general results where you impose much less on the initial data? Would there be some generalization?
Who are you? I'm sorry, I don't see you.
David,
David, okay, fine. This, I think, I never looked very carefully on this, but I'm looking at that, in fact, actually, with Emmanuel Trella for a question of population and opinion moving and graph limit stuff. But even for the regular mean field, I don't know if you start by something which is not a tensorial power of something. I don't know if there are some reasons. You mean starting by something which is still invariant by permutation, but not of the form of tensorial power? Is this your question?
My feeling is that considering tensorized initial data means that you have your n particles initially are drawn randomly with the same law and independently, right?
Yes. Absolutely.
While you could ask for, I mean, for the mean field limit, for sure there is deterministic results. So you just have to specify convergence of the empirical measure initially, which is much less.
Yeah, but you know, the problem is that what should be the result? I mean, the result should be the first marginal. It's okay, you can still define. Is going to be the solution of a Vlasov. Find that what would be the initial condition of the Vlasov you would have to take. probably the first marginal of the initial condition then.
Yes, definitely. You would probably need some, let's say, convergence of the k marginal of the initial data to some tensorized thing, but it should.
Okay. You mean yeah. Okay, you mean yeah.
Okay. It should be tensorized asymptotically, I guess, but there is no need to be exactly tensorized. So I was wondering if your extension with this potential, this chemical potential, would still be. I mean, of course, you would lose a lot of quantitative information, but at least qualitatively, if it would be okay.
I think yeah, some of the things should work. Yes, if I remember, if I go to the heart of the proof, but I didn't feel the details, so I cannot tell you exactly now. But I don't see any a priori obstruction.
Okay. Thank you.
Between that and the result, there is can be a long path. But
okay, thanks. Thanks a lot.
Is there any other question? Comments? Thierry, just concerning the, I have a question concerning the equation for the chemical potential. The fact that you use this convolution with chi for the chemical potential. Okay, yes. So I mean, a particular interesting case, I would say, it would be to take just the density in a space. So, which would mean that you are not taking any convolution with anything on the sum of Diracs, but really the sum of Diracs are only the positions. So the approximation of like the empirical measure associated to the density in a space. Do you see what I mean?
Yeah, so the source term should be an empirical measure, exactly.
I mean, in a sense, I mean, a particular interesting case would be to take just the sum of the Diracs at the positions.
Yeah.
Yes. So can you comment if what you think about that case?
Yeah, thank you for your question, because first of all, I think I'm quite confident it could work because the solution of the heat equation is explicit.
Yes.
And in fact, something I forgot to say is that I took this modelization of the interaction with the medium like this, but in fact, we use very few of it.
Yes.
A very little part of it. So it should work for a lot of other models. The proof is very stable. It uses very low property of the chemical chemical potential. So, however, whatever is the production of it, it should work. Yes. But what you propose is certainly interesting. Yeah, to put exactly the empirical measure. Yeah.
Yeah, because is what you expect, for instance, for that's an approximation of the density of the integral of FdV at the end there, giving you some production. I mean, it's one of the simplest case.
One of the simplest. But the fact that introducing the key, because you know the key means that in fact the source is a convolution of key with empirical measure.
Sure. I understand.
I think that there is a feature of the interaction which is all by this. But actually, it's certainly a question we should ask the biologist
Okay.
Okay.
Thank you. So, is there any other question? Okay, so if not, let's thank Thierry again. And we have an extended lunch break, which is thank you very much also.
Yeah,